Good day, students. Today we continue course of lecture in physics. You should have completed 2 labs by now. Please pay attention. Each group is divided into subgroups A and B. And each subgroup has its own teacher. It's very important to online students. Look at the table after first lecture and please remember your teacher for laboratory practice. You should submit your report and the answer to test question only to your teacher, because only he or she will give you a credit in physics. To get credit, you need to familiarize yourself with all the topics of lecture, take tests after each lecture, complete laboratory work online or offline, make a report on 6 laboratory works, answer to test question after laboratory works in a writing form. And that's all. Each teacher has the right to change the order of works, so only follow the laboratory assignments of your teacher. And now, our theme of lecture is the hydrodynamics of viscous liquid and the basic physical quantities of hydrodynamics. Volume velocity of current flow, Q, is equal to the volume of fluid which flows through the section of the tube of current per unit of time. And look at this expression where Q is equal to ratio volume divided by T. Linear velocity, V, is the path traversed by the particles of blood per unit time. Look in this expression for V, linear velocity. And then the relationship between the linear and the volume velocity. Q is equal area multiply V. S is a cross-section area of fluid flow. Pressure is a physical quantity which characterizes the intensity of a normal force with which one body acts on the surface of another. If the force exhibits a uniform distribution along the surface, the pressure is determined at the ratio of force to area. And look at this expression. This pressure, force, and area. F is the magnitude of the normal force on the surface, and S is the area of the surface. The C unit for pressure is a Pascal. Blood pressure, P, is a force exerting by blood per unit area of blood vessel. A stationary current of a liquid, continuity equation of flow filament. Hydrodynamics is a section of physics that studies question of motion of liquids and its interaction with environmental solid bodies. Liquid medium makes the greatest part of a human organism. Its motion provides metabolism and the supply of cells by oxygen and therefore mechanical properties, and the current of liquids represent interest for physicians and biologists. Consider the established or stationary current of liquid. As such current at which speeds of particles of liquid in each point of a stream do not changes. Stationary current is characterized by lines of a current. Look at the picture. This is a line of a current. And this vector is a velocity. It is the imagined lines conterminous to trajectory of particles. Tangents to lines of a current shows a direction of speed vector of particles of a liquid. Density of these graphically represented lines is proportional to speed. A part of a system of liquid limited from different direction by lines of a current forms a tube of a current or jet. Look at this picture. Tube or jet, and this tube or jet. Suppose incompressible fluid which fills completely a channel such as a tube and flow along it. Then if some amount of fluid enters one end of the channels, an equal amount must have the other end. The principle of continuity. Look at this picture. This is a volume V1 and area S1, and this volume V2 and area S2, and this velocity V1 and this velocity is V2. Flow rate Q is used as a measure of amount of fluid. It means a volume of fluid V which moves through the cross section of a channel per second. If the fluid enters one end of a tube at the flow rate Q1, it must leave the other end at the flow rate Q2, which is equal to Q1. Look here. This expression Q1 is equal to Q2. And Q is a ratio of volume divided by T. As a volume is a area section, and this distance L. And we know the displacement of the distance L divided by T is a velocity, and we get Q is equal as multiplied by V, and delta V is equal V. It is a constant. And again, V, big V is a volume, S is a cross-section area of a pipe, and V is the mean velocity of the liquid for a section. Let's allocate a tube of the current so narrow that speeds of particles V in its any section S perpendicular to axis of the tube is possible to count identical on all sections. As speed of particles is directed along a line of a current, then particles of a liquid cannot fall outside the limit of this tube. Then volume delta V of incompressible liquid proceeding through any section of a tube per unit of time remain the constant. And delta V is equal V multiply S area, it's missed, is equal constant. The parity express continuity equation of flow filament. Since only at continuous current through any section for same time pass identical volumes of incompressible liquid, then V1 multiply S1 is equal V2 multiply S2. Whence it's a ratio of area section is equal to ratio as velocities. Average speed of current in various sections of a pipe are inversely proportional to the areas of this section. From the continuity equation of law follows that also for a real liquid at the established current on a pipe of variable section, quantity of the liquid proceeding for the same time through any section of the pipe remains constant. Q is a constant. In particular, with big accuracy, it is carried out for blood current in large blood vessels in time equal to several intimate cycles directly following one after another. And then talk about a question of Bernoulli and its consequences. One of the most important equations used for the description of moving liquids for the first time was received by Swiss mathematician and physicist General Bernoulli. For deduction of the equation, Bernoulli has assumed that we deal with ideal liquid. It means that we neglect any forces of viscous resistance and friction. Let's consider stationary current of an incompressible ideal liquid. We shall allocate the volume of liquid limited by walls of a narrow tube of current and perpendicular to lines of current by section S1 and S2. Look at the picture here. S1 and S2. In time delta t, this volume will be displaced along the tube of current, and the border of volume S1 will receive displacement delta L1. This is delta L1, and border S2 displacement delta L2. The work made at it by forces of pressure is equal to the increment of total energy. It's a kinetic energy and potential energy in a considerate volume of liquid, and the work is equal to some kinetic and potential energy. But other way, we can write down work is force multiplied to displacement. Look at here, force and displacement, or pressure and area section. Forces of pressure upon walls of a tube of current are perpendicular in each point to the direction of moving of liquid, owing to what works do not meet. Work of force of the pressure enclosed to section S1 and S2 is equal to 0. This work is equal to look here, P1, S1, L1, but it's delta L1 minus P2, S2, and delta S, or delta L2. So this expression. Total energy of considerate volume of liquid is composed from kinetic energy and the potential energy in the field of forces of terrestrial gravitation. Owing to stationary current, total energy of that part liquids, which is limited by section 1 and 2, in time delta t does not change. Therefore, the increment of total energy is equal to the difference of value of total energy of the shaded volume delta V2 and delta V1, which mass is a product of rho is a density of liquid and delta V is a volume. Let's take section S of a tube of current and displacement delta T so small that all points of each of the shaded volume could attribute the same speed V, pressure P, and height H. Then for the increments of total energy, look here, the total energy. This the second volume and this first. Change of total energy is equal to the work of external forces if we disregard friction within the system. We can equate in both of this expression for the work, or this work, and this work. This work, it's a delta energy. We write down here, and this work we write down here. And we remember that mass is a product of density and volume. But the volume is an area multiply distance or displacement. And look at this equation and divide it by the expression S1 L1 is equal S2 L2. And in according to Bernoulli's law, the pressure in the flow is higher, where speed is lower, and vice versa. For steady rotational flow, the velocity, pressure, and elevation of an incompressible non-viscous fluid are related by an equation in a box. This expression in a box, where the P is a static pressure. Rho GH is a hydrostatic pressure. And rho V in square divided by 2 is a dynamic pressure. And this equation was discovered by Daniel Bernoulli. Bernoulli's equation proves that the total pressure is contained along the tube of current during steady state flow of perfect or ideal fluid. And the next, fluid viscosity. Viscosity is a property of fluids owing to which they oppose any motion of their neighboring portions relative to one another. Viscosity is created by internal friction between the molecules. Various fluids differ greatly by the value of their viscosity. For instance, the viscosity of oil is greater than that of water. Viscosity is a major factor in determining the forces that must be overcome when fluids are transported in the tube. Viscosity influences also the blood flow in the circulatory system. In an ideal fluid, there is no viscosity to hinder the fluid layers as they slide past one another. Within a pipe of uniform cross-section, every layer of an ideal fluid moves with the same velocity, even the layer next to the wall. Look at the figures A and B. A, in ideal non-viscous fluid flow, and B, in viscous flow, the speed of the fluid is zero at the surfaces of the pipe and increases to a maximum along the center axis. When viscosity is present, the fluid layer do not all have the same velocity as a part B of the drawing illustrates. The fluid closest to the wall does not move at all, while the fluid at the center of the pipe has the greatest velocity. The fluid layer next to the wall surface does not move because it is held tightly by intermolecular forces. In a real liquid, between molecules operates the forces of mutual attraction, causing internal friction or viscosity. Internal friction, for example, causes force of resistance at stirring of liquid, slow down speeds of falling body thrown in it. And Newton has established that force F friction, of internal friction between two layers of liquid moving with various speed is directly proportional to area of adjoining layer and to gradient of speed between them. The gradient of speed between layers is a change of speed divided to length. dv, look at here, dv divided to length, dy, in the direction perpendicular of speed. And this speed and gradient is perpendicular to speed. Fundamental law of viscous liquid was discovered by Newton. And look at the expression in a box. It's in Newton's formula. And F friction is equal minus eta. It's a gradient of speed multiply area. This area, this force, and where eta is a coefficient of viscosity or dynamic viscosity. Eta is a dynamic viscosity and equal to the force of internal friction that acts on the unit area of the layer's surface at the velocity gradient, which is equal to 1. See units of viscosity is Pascal seconds. Eta in Pascal seconds. Common units of viscosity plus 1 plus is equal to 0.1 Pascal second. The gradient of speed is which characterized the degree of change in the velocity of the liquid flow in a transfer from one layer to another. The viscosity of blood. Eta norm is equal, it's a range from 0.004 to 0.005 Pascal seconds. It's a norm. And the viscosity of blood pathology, for example, it may be anemia or polycythemia. It's from 1.7 to 22.9 micropascal seconds. And now talk about Newtonian fluids and non-Newtonian fluids. The fluids whose viscosity may be defined by Newton's equation, and look at the expression in a box where F friction proportional to gradient of speed are called Newtonian fluids. For Newtonian fluids, the coefficient of viscosity eta depends only on temperature and nature of fluid, and does not depend on conditions of fluidity. They are homogeneous fluids such as water, spirits, solution of electrolytes, mercury, glycerin, etc. There do exist more complicated heterogeneous fluids for which the Newtonian description is inadequate. The coefficient of viscosity of these fluids depend on conditions of fluidity. They are called non-Newtonian fluids. They include some suspensions, emulsions, foams, protein solution, polymer solution, blood. Relative viscosity is equal to the ratio of the coefficient of viscosity of the given fluid to the coefficient of viscosity of distilled water at 1 and the same temperature. Look at here is a relative viscosity. Viscosity of distilled water at room temperature is approximately equal to 10 in minus 3 Pascal second. Kinematic viscosity is a kinematic viscosity is a nu. It is a ratio of viscosity of fluid to its density. It's a ratio of dynamic eta, dynamic viscosity to density. Viscosity of liquid is measured with the help of viscosimeter. Look at here, it's a viscosimeter and it's laboratory work number 3. With help of capillary viscosimeter of Oswald, look at the picture, it's possible to measure viscosity of gases and liquids in the U-shaped tube, one of which knees has a capillary tube. Pour a researched liquid with the help of a rubber pier, but it's a here a rubber pier. The liquid from the big tank 3 is sucked in the tank 1 above mark A. This mark A and mark B. And this fluid goes to the tank 1 to mark A. Then, having removed the pier, is a measured time of flow of liquid between labels A and B. Comparing this time with time of flow of reference liquid, distilled water, can be determined viscosity of research liquid. Method of incident blob is used the viscosimeters which has been set up on the Stokes law. Measuring the viscosity of the blob, it's possible to find viscosity of a liquid. And the dependence of viscosity coefficient, it's about dynamic viscosity, not dynamic, is found by this temperature is found by Frenkel and Rada equation. And to look at the box, it's a Frenkel and Rada equation, where C is a constant, K It's a Boltzmann's constant, and W, it's activation energy. Viscosity quickly diminishes with the temperature growth T. At a higher pressure, the liquid viscosity quickly rises with the pressure increase. This is associated with the activation energy increase. And then talk about laminar and turbulent flow. In each fluid's layer slips over the other. Different layers do not get mixed. Then the flow called laminar. The velocity of flow at any point on fluid remains stable. The streamlines do not intersect each other. The other kind of flow is named turbulent. The turbulent flow is unstable. The flow of liquid is cold and all layers of liquid mixed. The turbulent flow needs more energy than the laminar one. English physicist Reynolds investigated the condition under which a flow becomes laminar or turbulent. The transition from laminar flow into turbulent one depends on the value of dimensionless quantity called the Reynolds number. The Reynolds number. Look at this expression in a box where V is the average velocity of flow and D is the diameter of tube, rho is the density of fluid, eta is the dynamic viscosity of fluid. The transition from laminar to turbulent regime of flow is indicated by a critical Reynolds number, which depends on the exact flow configuration and it is determined experimentally. The critical value of Reynolds number for cylindrical tubes at which laminar flow turns into turbulent is 2000 or 2400. And if the Reynolds number less than 2000, it's it is a laminar flow, and more than 2000, it's a turbulent flow of liquid. And the Stokes law. Look at the picture, and when we have a tube with a glycerin and the body falling down in this liquid, and for this body three forces. First, the force of gravity, it's a W. It's a gravity is equal mass multiply by free fall acceleration. And we can write down mass as is a product of density and volume. And this raw ball is a ball density. And second force, the buoyant force, Archimedean force, is equal rho G and V, where rho liquid is the liquid density. And third force, it's a Stokes force, and is equal 6 pi, it's a dynamic viscosity, R V is a coefficient internal friction, it's a dynamic viscosity, eta. And use a second Newton law, we can write down this expression, and write down in the next step each of these forces here, and acceleration is dv by dt. And when this body falling down with constant velocity, we can write down is a constant, and this expression will be 0. And from then next step, we can write down a dynamic viscosity with t, it's time, and L it's distance which body moved from one mark to another. It can as a speed, and this expression to determine a dynamic viscosity, it's the Stokes method. And then talk about the physical basis of hemodynamics. Blood circulation is one of the most important processes occurring in a human organism. The section of biophysics studying law of motion of blood on the vascular system is named hemodynamics. General laws of current of liquids investigated by hydrodynamics are established within the framework of classical physics and are the basis for description of complex hemodynamics processes in a human organism. However, properties of blood in many respects are different from properties of liquids used in engineering, and having elastic walls and repeatedly branches blood vessels considerably differ. For example, from system of water pipes. Therefore, the biophysics considers only a simplified model of blood circulation. the human cardiovascular system. Hemodynamics study the motion of blood in the circulatory system. One of features of physical model of cardiovascular system is the elasticity of its walls. Elasticity is the ability of material to test more or less significant elastic convertible deformations at rather small efforts. Walls of blood vessels differ on its structure. Aorta and large arteries have the walls consisting from muscular fiber, elastin, and collagen. Elastin supposes deformation up to 200 or 300%, collagen up to 10%. 10%. Arterioles consist completely only of muscular tissues, which extensibility is much less. Walls of capillaries are not covered by elastic or muscular tissue. Here is a list of true facts about the human cardiovascular system. The heart, illustrated in the schematic in figure, is the pump that drives blood through your blood vessels. The blood vessels are differentiated into three distinct types. First, it's arteries, which lead strictly away from the heart and which contain a muscular layer that elastically dilates and contracts the arteries in synchronous way to help carry through surging waves of blood. This acts as a shock absorber and hence reduces the peak systolic blood pressure. Arteries split up the further one is from the heart, eventually becoming arterioles, the very small arteries that actually split off into capillaries. Second, capillaries, which are a dense networks of very fine vessels that deliver oxygenated blood throughout all living tissue so that the oxygen can't dissociate it from the carrying hemoglobin molecules and diffuse into the surrounding cells in systemic circulation or permit the oxygenation of blood in pulmonary circulation. Third, veins, which lead directly back to the heart from the capillaries. Veins also have a muscle layer that expand our contract to aid in thermoregulation and regulation of blood pressure is one lies down or stands up. Veins also provides capacitance to the circulatory system and store the body's spare blood. 60% of the body's total blood supply is usually in the veins at any one time. Most of the veins, especially long vertical veins, are equipped with one-way venous valves every 4 or 9 centimeters that prevent backflow and pooling in the lower body during diastole. Blood from the capillaries is collected first in venules and then into veins proper. There are two distinct circulatory systems in humans. and in the rest of the mammals and birds. Systemic circulation, where oxygenated blood enters the heart via pulmonary veins from the lungs and is pumped at high pressure into systemic arterial, then deliver it through the capillaries and back via systemic veins to the heart. Pulmonary circulation, where deoxygenated blood that has returned from the system circulation is pumped into pulmonary arteries that deliver it to the lungs, where it is oxygenated and returned to the heart by means of pulmonary veins. These two distinct circulations do not mix and together from a closed double circulation loop. Blood pressure is generally measured and transported in terms of two numbers. First, systolic blood pressure. This is a peak maximum arterial pressure in the wave pulse generated, then drives systemic circulation. It's measured in the arm where it is supposed to be and reasonably accurate reflection of peak aortic pressure just outside of the heart, where sadly it cannot easily be directed to measure it without resorting to invasive methods that are in fact used during surgery. Diastolic blood pressure. This is through minimum arterial pressure in the wave pulse of systemic circulation. Normal systemic blood pressure can very accurately be estimated on the basis of the distance between the heart and the feet. A distance on the order of 1.5 meters leads to a pressure difference of around 0.15 atmosphere or 120 millimeter of AAG. Blood is driven through the relatively high resistance of the capillaries by the difference in arterial pressure and venous pressure. The venous system is entirely a low pressure return. Its peak pressure is a typical order of 1 or 0.008 bar. This can be understood and predicted by the means the distance between valves in the venous system. The pressure difference between one valve and another, 8 centimeters higher, is approximately 0.008 bar. However, this pressure is not really static. It varies with the delayed pressure wave that causes blood to surge its way up, down, or sideways through the veins on its way back to the atria or the heart. And talk about Korotkov method. Blood flow in the circulatory system is laminar. In aorta, it may become turbulent during a physical work which greatly increases velocity of blood. Blood flow may be turbulent also in arteries, the cross-section area of which is diminished by some pathological process. And Reynolds number for blood 2000, and critical Reynolds number for water, it's 2300. It's for water. And where Reynolds number is small, then critical, the flow is laminar. When Reynolds number is large, the flow is turbulent. The change of blood viscosity value may be diagnosed owing to turbulent noise. It may be explained by the fact that at anemia viscosity coefficient decreases by a factor of 2 or 3 and even more. Correspondingly, Reynolds number increases since approximate 1 divided by eta, divided by dynamic viscosity. As a result, Reynolds number becomes greater than its critical value, and transition from laminar blood flow to turbulent one takes place. Medical application of transition between laminar and turbulent flow of blood is connected with measuring of blood pressure by Korotkov method. In accordance with this method, systolic upper pressure is measured at the moment when blood begins to squeeze through the hole in arteria compressed by the cuff. Look at the picture. It's a pressure cuff. Exactly at this moment, noises appear resulting from turbulent flow of blood. This sound first heard, and the sound disappears. It's a not sound, no sound. And what happened with arteria? When you can see in this picture, when arteria is open and when it's closed. Diastolic lower pressure is fixed at the moment when the stenosis disappear as a result of release of cuff and transition of flow from turbulent to laminar. And talk about atherosclerotic plaque partially occludes a blood vessel. And look at this picture. Atherosclerosis granular deposits of fatty material called plaques that attach to the walls of e.g. arteries and gradually thicken over time, generally associated with high blood cholesterol and lipidemia. The risk factors for atherosclerosis form a list as long as your arm, and its fundamental causes are not well understood. Although they are currently believed to form as an inflammatory response to surplus low-density lipoproteins, one kind of cholesterol in the blood. In figure 2, arteries are illustrated. It's a normal artery and narrowing of arteria. A and B. And the arteria A is clean. Look at this picture. It's clean. It's a cross section, and this cross section is clean, has a radius R1, this radius. Has a very low resistance to any given flow of blood because is a radius over the length L, this L is low. There is a very little pressure drop between P plus, and to look at this picture, P plus and P minus on the two sides of any given stretch of length L. The velocity profile of fluid is also more or less uniform in the arteria, slowing a bit near the wall, but generally moving smoothly throughout the entire cross-section. And artery B has a significant deposit of atherosclerotic plaques that have coated the walls and reduce the effective radius of the vessels to R2. Look at here, this R2 is a radius over an extended length L. The vessels is perhaps 90% occluded. Only 10% of its normal cross-section area is available to carry fluid. We can now easily understand several things about this situation. First, if the total flow in arteria B is still being maintained at close to the levels of the flow in arteria A, the fluid velocity in the narrowed region is 10 times higher than normal. Since the Reynolds number for blood flowing in primary arteries is a normal around 1000 to 2000. Increase V by a factor of 10 increases the Reynolds number by a factor of 10, causing the flow to become turbulent in the obstruction. This tendency is even more pronounced than this figure suggests. Is drawn nice symmetric occlusion, but the aphtharoma is more likely to grow predominantly on one side, and irregular lesions are more likely to disturb laminar flow in for smaller Reynolds number. This turbulence provides that basic for one method of possible detection and diagnosis. You can hear the turbulence with through the stethoscope during a physical exam. Physicians get a lot of practice listening for turbulence, since turbulence produced by artificially restricted blood flow in the branchial arteria by means of a constructing curve is basically what one listens for when taking a patient's blood pressure. It really shouldn't be there, especially during diastole, the rest of the time. The Korotkov method, it's laboratory work number 4. You can do physical exercises only once, and the physical exercise it upstairs to 7th floor and back to laboratory, and then you can measure your diastolic, systolic pressure and the pulse. Plot a graph how this diastolic and the systolic pressure and the pulse relaxation versus time. And you, in the end of the work, you have to write down conclusion. You have to describe your relaxation, character of relaxation, diastolic and the systolic pressure and the pulse, and compare your result after physical exercises and your result before physical exercises. And that's all. Thank you for your attention. Our lecture is finished. And what about your homework? Your homework, read a lecture. I will open a lecture at PDF format today. And take the test after lecture in 2 weeks. I will open the test for you tomorrow. And don't forget, it's an offline student. Don't forget about laboratory practice and visit our lessons and do your laboratory works and design your report and answer test question in notebook, 3 questions in notebook in a writing form, and bring it next class. Okay, thank you for your attention. Goodbye.